So it's now my distinct pleasure to introduce to you the 2019 Royal Society of Canada Miroslaw Romanowski Lecture, given by Professor Keith Hipel. The Royal Society of Canada offers a variety of very prestigious medals and awards, recognizing the outstanding achievements of Canadian researchers, of which Professor Hipel is one. So earlier this year, Water Institute member Professor Keith Hipel was awarded the Miroslaw Romanowski Medal for his significant contributions to the resolution of global environmental problems. And the medal is one of Canada's most prestigious environmental awards. So I'm going to give you a little bit of background information about Professor Hipel before he starts his distinguished lecture. As you know, he's a professor, university professor in the Department of Systems Design Engineering. He was the past president of the Academy of Science within the Royal Society of Canada, senior fellow of the Center for International Governance Innovation, and fellow of the Basile School of International Affairs here in Waterloo. Professor Hipel is globally renowned for his unique interdisciplinary research on the development of conflict resolution mechanisms, multiple criteria, decision analysis, time series analysis, and other decision-making methodologies for addressing challenging what he calls system of systems engineering problems, lying at the confluence of society, technology, and the environment. Professor Hipel is a highly cited researcher. He has written 5 books. He's published 327 papers. That got over 14,000 citations. He's a respected teacher and mentor. He has supervised 35 PhD students, 47 master students, and he has taught over 5,000 students in Canada and another 1,000 students overseas. It is a long list, bear with me. Professor Hipel has received numerous accolades for his highly original and policy-relevant research, far too many to cite, but I want to give you a few examples of Professor Hipel's appointments and awards. He is the foreign member of the United States National Academy of Engineering. He was awarded the Eminent Scientist Award from Japan Society for the Promotion of Science. He was awarded the Jiangsu Friendship Medal and has 5 honorary professorships in China. He has honorary doctorate degrees from 3 different countries, including Canada, France, and Hungary. And finally, earlier this year, Professor Hipel received Canada's highest civilian honor from the Governor-General of Canada when she appointed Keith as Officer of the Order of Canada. Please join me in welcoming Water Institute member and the 2019 Royal Society of Canada Miroslaw Romanowski winner, Professor Keith Hipel.
Thank you, Roy, for your very kind introduction. Nice to see so many nice people here today. Before I start, I'd like to introduce Professor Flora Ng from Chemical Engineering. Flora, if you could stand. She's a university professor and a very famous researcher here. About 3 weeks ago, her husband, Gary Rempel, passed away, and Gary was one of our best professors at the University of Waterloo. He was also a former president of the Academy of Sciences within Canada, and also a member of the Order of Canada. So if I may, Flora, I'd like to dedicate this presentation to Gary's fine memory. He left a real impact on the University of Waterloo. So this is the title of my presentation, Negotiation over Groundwater Contamination. As you can see, I'm involved with a number of organizations, and let me just mention a few that I'm right down here. I'm very proud to be a member of the Water Institute. And these institutes form a wonderful service at the University of Waterloo. How many here are members of the Institute? I assume all of you. And where are the members of your staff then, Roy? If you could stand up, please. Who else is there? Yeah. Round of applause for the people who give us such a good service. I know it's a lot of hard work, and we really appreciate that. Everything that I'm going to talk about today, I wouldn't be able to speak about if it weren't for the excellent students and colleagues who I've worked for over the years. Here's a photograph of part of the team. This was taken 3 years ago near the grad house. How many know where the grad house is? Perhaps Roy will take me there afterwards. I don't know. Or everybody. So I've been very blessed to be able to work with such fine people over the years, and all this work that we've done over the years is largely due to them. It's been my honor to work with them. Let me mention just some of the things that we've been working on. This is a citation that they published. So we're taking a look at a number of different systems thinking methodologies. First of all, notice we look at both the physical and societal systems aspects. Without looking at both of those together in an integrated way, you're really not solving a problem. We like to say it's not real engineering. When I say societal, I'll also include things like economics, conflict, value systems, and all the rest of it. So we have to look at both of them together. You just think of things like climate change, very heavily dependent, especially on the societal part. In terms of other things, we like to look at things in a sustainable, integrative, adaptive fashion and be fair to the stakeholders in the system. Very, very fair. Value systems and fairness we like to embed in all of our models. Some of the specific techniques that we've looked at over the years, one is conflict resolution. That's what I'm going to speak about today, just to give you a taste of the types of things we're doing there. But we also work in a lot of other related areas, multiple objective decision making, stochastic hydrology, environmental impact assessment, and equitable water allocation, everything within a systems engineering viewpoint. We think it's important that you see the big pictures. You have a system there, one there, and you have to look at them in an integrated way. So that's just a summary of what we've been doing. I'll just look at one aspect. This is Dr. Sylvie Romanowski. She's actually the daughter of the professor who very kindly donated the money for this award. It's very generous of him. And it's given out once a year. I think there are a lot of really excellent researchers at this university. Don't hesitate, let's say people like Roy and myself, to make sure that we nominate very worthy people. She was actually in Halifax a week and a half ago where we had our annual meeting of the Royal Society of Canada. That's a photograph taken there. Yeah, this was actually the first Romanowski lecture that was given in Halifax about 12 days ago. On the left we have Eric Meslin. He's the president and CEO of the CCA, Council of Canadian Academies. How many have heard of that organization? CCA. They actually then get money from government and industry to take a look at special projects. Now the talk I gave there was actually different from this one. I have a number of them that I give in this topic, and it had to do with energy use and climate change. And there we were taking a look at how can you actually solve this problem. We got experts from across Canada, a few from the United States, there were 8 of us in total, and we spent a year looking at this problem. We didn't do any new research. We brought sort of research from there, over there, bring it all together, and then come up with some suggestions how to solve the problem. Let me just briefly mention what those are. Given the importance of climate change at the present moment, as you know, a report just came out in the United States, a number of other recent reports on how serious this problem really is. This is really a time for action. No more talking about it, does it exist? Well, let's look at the theory a bit more, develop better energy efficient machines and all the rest of it. We need action. And the nice part was in this report, we actually came up with 3 main recommendations or findings. Number 1, all the technology already exists. It's on the shelf, ready to go. It's not all that costly. Of course, it costs a bit to change systems. For example, in Ontario here, we have the CANDO reactor, one of the best designs in the world. Probably nuclear power plants would be needed in order to take up the slack in the electrical, let's say fill the gap in electrical demand as we close down all our coal-fired plants, and also, of course, the natural gas plants that may replace them temporarily. Number 2, decarbonate the grid. That means shut down all coal-fired fossil fuel plants almost instantaneously. This produces about 1/3 of the greenhouse gases, and we have to take quick action there. Here's a little quiz. How many here are environmentally conscious? Okay, quite a few, good. Okay, here's a quiz. Let's say if you wanted to buy a new car and you wanted to be environmentally responsible, what is the worst possible car you could buy, let's say in the Northeast United States, most of China, and a few other countries like that, Japan, at the current time? What's the worst possible car in terms of greenhouse gas emissions? Anybody want to guess? A truck? Let's say it's just a vehicle for personal use. Yeah, trucks do emit, of course, more greenhouse gases. Sorry? Electric vehicles. Who said that? Electric. Oh, come down here. You get a prize. Now you're going to have to answer why. You already won an award.
Because of the batteries. And because we are getting the electricity from the fossil fuels from the beginning.
Exactly. Round of applause for the show. No, come here, come here, come here. Don't run away. So, the Department of System Design Engineering, we're celebrating our 50th anniversary this year.
Yep.
So here's a collector's item, one of our pens from the department.
Thanks a lot.
Tell them about yourself for a minute.
Okay.
Tell them the research you're doing.
So I'm doing a research in failure analysis of complex engineering systems, and the application is hydropower dams and the nuclear waste management for the first nuclear repository that will be in Canada 30 years from now, hopefully. So we are doing some prediction methodologies of how to predict the failure ahead in time.
Okay, very good. Congratulations. It's amazing the amount of interesting work that goes on. For you, those of you who like looking in streams, if you overturn a rock, you never know what you'll find underneath it. And that's why I think it's good to have these institutes, because it sort of brings people together in a common forum and you can share ideas. Okay, so as I mentioned then, number one, we have the technology there, it already exists. We do recommend further research. Number two is you have to decarbonize the grid. Number three is probably the most important obstacle at all. Does anybody want to guess, what do we really have to do in order to get climate change under control? What's the key item?
Social events.
Sorry?
Social events. I think that's still lacking.
I think that's close enough. Come up here. Yeah. So congratulations. Here's a 50th anniversary pen. Now tell us about your research, please.
Like Anna, I also work with Professor Kuhn on the nuclear waste research. Except that his is downstream research of what coordinating the other friends do. We work on looking at the aspect of how long will these engineered barriers and deep geology and repository system actually survive. So we're looking at it from a microbial corrosion aspect, chemistry aspect.
Oh, congratulations. Very good work. Yeah, let me just express that slightly differently. What we need is economy-wide policy. And of course, what they're trying to do internationally, we need it right around the globe. We need an agreement that we're going to cut back very drastically. We basically need 100% cutback by the middle of the century, but there's no reason why we can't now start cutting back very, very drastically. In our report, we found that the costs are very manageable. If somebody comes along and says, well, this is going to cost us far too much, just say the evidence does not support that at all. As a matter of fact, when we look at the reports in Canada, these are reports by the government, industry, published papers from reputable sources. Canada could cut back 60 to 90% at manageable cost of our CO2 emissions right now from all sources, vehicles, industry, domestic, and all the rest of it. So we can do it. It's just a matter of political will to make sure it's right across the country. Now, to get even more practical, we're engineers and we like to solve problems. Take a look at the political party that you want to vote for in the next election. If they do not have an economy-wide policy, such as, let's say, a tax on carbon, cap and trade, whatever it is, right across the economy, they don't deserve your vote. And let them know, if you want me to vote for your party, we expect you to be responsible. As a matter of fact, when people asked us after this report came out just 2 or 3 years ago, what is the best thing that I could possibly do? It's go speak to your member of parliament and make those people give us proper action. Because the solutions are there and we can do it now. So that's just a summary of another talk that I give related to this, but I thought it was so important given the current situation. I just wanted to mention it briefly today. Okay, so there's a happy group right there. So that's President Feridun Hamdulapur and John Thompson on the right and left. He just became a specially elected fellow of the Royal Society of Canada because of some really good work that he's doing, especially getting more female professors and students in the STEM areas. Very, very important, I think, to people around the world. And of course, that's Professor Romanowski. She's actually retired from Northwestern University in Evanston. So objectives. Here's what we'd like to do. I'm just going to take a part of our work today. This has to do with conflict resolution, something we call the graph model for conflict resolution that we developed here at Waterloo, and just try to explain how it works, just so you have a taste in your mouth. Afterwards, you may say, hey, I want to have the full meal, and it may be useful to you somehow later in your research. I also mentioned at the bottom there the importance of the physical systems input. This can affect the preferences of the decision makers if you have really credible evidence and information from the physical system side, and also things like economics, very important when you're making strategic decisions. So here's let me just pass these around. I actually brought a paper along. It covers the application I'm going to use to show some ideas. So I'll just refer to this as I go on in the talk. Some of the items are covered here. So for example, this whole idea of the societal systems models and physical systems models. We now are developing really good modeling techniques. They've been there for a long time in the physical sciences. In the societal, let's say, societal systems models, there we still have a lot of progress to make. But the fact is we have some really good models that can aid in decision making. If you take a look at the first page in the paper there, we have a discussion about that. Like I say, I tell our students in engineering, if you don't look at both of those, that's not real engineering. If you don't look at both of those, that's not real social sciences. You have to really look at both of them together. Almost everything these days is interdisciplinary. So the example that I'm going to use today has to do with an aquifer contamination problem, possibly the second most important type, or let's say serious type of environmental problem occurring today. An obvious one, of course, is climate change, with having too much carbon in the atmosphere and not at other locations in the carbon cycle. It's in the process of destroying our climate. It's as simple as that. Another one is sort of the dumping of bearing of chemicals in the ground, including chemicals of emerging concern that we don't even know what the effects are going to be. And the way that could pollute the underground aquifers, who knows, for centuries or thousands of years into the future. This is a major problem worldwide. Unfortunately, the newly industrializing countries and now great mighty powers like China and Japan, an industry they're no longer developing, they're already there. They passed the line about 10 years ago, China. Well, they didn't learn from us, unfortunately, and they're still making the same mistakes that we made. So I'm going to use that as an example then to demonstrate how this methodology works. In our research group, we like to use, let's say, practical examples to inspire us to develop new methodologies, because you're hoping they'll actually serve some useful purpose. So in this aquifer problem, we'll take a look at the societal level. That's where we can use things like game theory. And then down there in the physical or environmental realm, then there are other types of models that we can use. So what we really want in a situation like this is the information you get here can feed into the societal level decision making. Now, how many here actually do some work connected to water? Okay, almost everybody. Well, I think that you should give yourselves a round of applause, because some of the best societal and management models have been developed in the water resources and environmental literature. You take a look at some of the procedures that have been developed, let's say in integrative adaptive management, for example, in economics having to do with the environment. The 2 Nobel Prize winners this year had to do with environmental economics. There's a heck of a lot going on. As a matter of fact, probably, I shouldn't say this too loud, but probably the people working in business and say management in general might want to take a look at the water resources literature. But anyway, that was the literature that inspired us to try to carry things even further. So just to repeat again, we want to span both the societal and physical system realms, and everything, almost everything is interdisciplinary. So what are some of the accomplishments? Societal decision analysis tools, physical, chemical, and biological systems tools. And right at the bottom here, what's happening a lot are what are called decision support systems. You simply take your research ideas here, develop certain algorithms so you can apply them, and then over here, you write a user-friendly computer program so they can be implemented by others. This is a big contribution because you don't have to reinvent the wheel. I also teach a time series analysis course, and I remember not too long ago, maybe as little as 15 years ago, it might seem long to you, we never had programs available to estimate the parameters in a lot of the models that we describe. Now, fortunately, there's some excellent decision support systems, like R, for example, where you can use these models immediately to look at your data, interpret the results, and then try to get some insights for better decision making. So they are extremely important then for us to get work done. In other words, you can really focus on the problem at hand and really decide what to do. Formal decision-making models in general, these are ones that really go beyond, let's say, just talking about a problem in a sensible way. Two key areas where they've probably been developed. One is operational research. How many have heard of operational research? These are basically the mathematical models and systems techniques that were developed, starting to develop just before World War II. The British were afraid that they could possibly be bombing at the UK from Europe. At that time, Germany was becoming the most powerful military and economic power in the continent, and there was fear there could be attack. So they developed radar, both sides did, in order to protect themselves. Well, it ended up when they had a trial run against England. Over here in France, they put the British and French Air Force there. Then they had a mock run against England. They had all of these radar stations set up, and the whole experiment was a total failure. They were trying to predict, of course, where these planes might go in this trial run. Does anybody know why those experiments failed? The trial run was more than an experiment. It was an actual live experiment, let's say. Anybody want to guess why they failed? Okay, well, it had to do with communication. All of these separate radar stations, about 38 of them, got signals. Aircraft are coming from France over to England. They picked up the signal, but they failed to communicate across the radar systems and then try to predict where they were going to bomb, which industrial area, for example. So what they did was the British High Command said, let's look into the operational aspects of radar systems. And that's where operational research came from. During the war, it was extensively used by the British and the Americans especially, and also the Canadians. And then after the war, it spread into other areas, one key area being water resources. A number of the original ideas came from Harvard University, where they wrote a number of books, and they introduced operational research, and I'll mention systems engineering in a minute, into the water resources management area. So we have a lot to, unfortunately, often the good ideas happen under warfare situations. So here then we have then systems engineering. It took exactly what it says right there, a systems approach. This largely developed in NASA and a number of other organizations related to NASA in the United States. Much more general. It got into societal stuff a little bit more, looking at sort of integration across systems, connection among systems, and that was systems engineering. So a wealth of literature available there. Like I say, the main group that then took up the torch after the war was probably civil engineering and water resources. So how many have used game theory a little bit? Okay, that's one area of, let's say, a set of tools that you can say arose from systems engineering and operational research. It can be a little bit confusing if you go to the literature. So up here we have, let's say, the overall field of game theory. How are you going to sort it out? Well, here's one way to do it. On the left here, we have non-quantitative approaches, and over here, quantitative. Now, both approaches, by the way, are 100% mathematical. Mathematics is a science of relationships. Where they differ, these don't deal with numbers. They deal with logical statements, moves and counter moves, why things are stable, why they're not stable, according to logical interpretation of what's happening. Over here, it's more quantitative calculations. For example, you calculate expected values. Another way to look at it is, I'll mention this later on in a few minutes, there we take a look at relative preferences. So let's say after my talk here, Roy may say, well, Keith, let's go to the grad house. Would you like to have a Coca-Cola or a beer? So being an engineer, I may say, well, Roy, I prefer to have a beer. But if I said to Roy, beers were 6.54, and let's say Coca-Cola 2.1, he might say, well, goodbye, Keith, I got to go home. We simply don't think that way. When we get to these social conflicts, it's just sort of relative interpretation. Yeah, so I prefer to have a tea or a coffee or a beer over Coca-Cola. That's the only preference information that's required by these approaches. For those of you who do some work in classical game theory, if you have cardinal utility values, which we have over there, it's no problem. Because let's say the ordinal or ordering is always part of it. So we're mainly working in this branch right here. There's a technique called conflict analysis we developed at Waterloo. And this is a carry-on and big expansion of those ideas. Over here we have something like extensive form. This is the quantitative side. That can be quite useful at times. We use that in compliance problems. How do we know if a company is cheating and dumping its waste into a receiving body of water when nobody's looking? So we developed compliance models. How do you increase the probability so you catch an offender? Let me just mention one more area over here. This is cooperative game theory. Cooperative game theory is you're given a pie. How do you divide it up fairly? So for example, you can get benefits from bringing water by pipeline from Lake here into this area. How do you share the costs fairly? How do you share the benefits fairly? So let's say we have a pie here. Both Roy and I are really hungry. How would we divide the pie fairly between the two of us? What do you think? Sorry? Average. Average? That's sort of getting, in other words, cut it in half. But what if I cut the pie? Will Roy be happy?
I trust you.
Oh, he trusts me. Okay, well, you're a good human being. But let's say you don't trust me. How can you divide a pie fairly? In two pieces only.
As contribution.
Sorry?
As contribution.
Contribution?
Who contribution a lot to make the pie?
Okay, well, I think it's close enough. Come down here and then I'll... Yeah. So Jasmine, please introduce yourself to the group here. Here's a pen.
Okay.
Congratulations, yeah.
My English name is Jasmine. Chinese name is Yuhan. I'm an international visiting graduate student who come from China. I will start with Hipel in a year. Thank you.
Yeah, okay, thank you. I think what she said, when you have a pie and you want to split it fairly, one cuts and the other chooses. Now it ends up, if you try to cut it in 3 equal pieces, 4 equal pieces, any finite number, it becomes a very complex mathematical problem. So in water allocation, we somehow want to divide water fairly among competing users in a river basin. Well, for fairness, we use ideas from cooperative game theory. We use ideas from economics, so we understand the economic situation, let's say between industry, farming, domestic use, and all the rest of it. And then we have the physical system, the hydrology of the river basin. We put all of that together in one large optimization model, and it's amazing how well these techniques work. Dr. Chow, where is he? Yeah, he's actually taking a look at this whole idea of fairness, and he's taking a look at the demand side of it at the present moment in his research. And I'm sure this problem arises in the types of things that Roy looks at over here. So anyway, there are a lot of useful techniques. Here's what our decision support system would look like. Here we have the input subsystem. In a minute I'll mention when we look at a conflict, we have to know who the decision makers are, what could occur, what are the moves that could be made. Here's an analysis engine. This is where we do the moves and counter moves. I'm taking part in a conflict. Excuse me. I have a possible unilateral improvement. I can improve on my own. Can the others block it credibly? So sort of like chess playing here. And then over here, this is where we get our results and take a look at what it means to have very stable output and also resolutions or equilibria. I'll explain that in a minute. So the problem we're going to take a look at is right here in southern Ontario, the town of Elmira, Ontario. Here's another view of the same area. Elmira is about there. And yet another view, here's Waterloo County. There's the city of Waterloo, and there's Elmira. How many have been to the Elmira Maple Syrup Festival? Okay, quite a few. You're good. So here it is. Let's take a look then at this problem. It has about 7,500 residents. The water previously came from an underground aquifer. And in 1989, the Ontario Minister of the Environment discovered the aquifer was contaminated by NDMA. So that's a carcinogen. It can cause cancer. That hit the front pages of the newspapers for months. as soon as the Elmira citizens found out, they said, there's no way we're going to drink that water. Eventually, the solution is still taking water by pipeline to Elmira today, even though only some of the wells were contaminated, not all of them. So Uniroyal Chemical was immediately suspected as being the culprit. Here's the plant right here. It's now owned by Lanxess. It was originally owned by Uniroyal when this took place, this pollution problem. And then Chemtura took over, and now a German company just recently took over Chemtura internationally. That's actually from the roof of a consulting firm looking over on the chemical plant. A little bit more then about this conflict. The Ministry of the Environment, by law, they could issue a control order. Uniroyal then appealed the control order. The local government, the regional municipality of Waterloo and the cities, they brought in consultants. They spent millions of dollars taking a look at. They would drill holes down, see where the plume has spread to from where the pollution source is. So they knew where the source was. It was at the chemical plant. They'd buried a lot of barrels over the year with pollutants in it, still dumping at that time pollutants into the local stream. So they wanted to check how far has this plume spread. That's very expensive, but also very informative. So we wanted to take a look, let's study the negotiations using some of our conflict resolution methodology. There's another view of the plant. You can see that that's a Mennonite's farmer's fields in the background right there, and that's part of the old factory. That's a house just across the street from the chemical plant. It's quite a nice, pleasant city, the town of Elmira. There's a location once again. There's some of the plants from the air. Okay, what we're going to do now, I'll split it up into two main stages. First of all, what are the key parameters we need in the model? And then secondly, we're going to sort of take a look at the chess play, the moves and counter moves. They want, of course, the company to clean it up. Well, they may try to get out of that. The regional municipality of Waterloo, the local government, they, of course, could put a lot of pressure on the company. And then we have the environmentalists and all the rest of it. So here's sort of the notation for writing down a game when you're looking at something. All models are really just a language of communication. Sometimes you might take, let's say, a mathematics course and you think it's difficult, but the purpose actually is to make things simpler. So this hopefully makes things simpler. Here's the language we use to display what's happening. So notice on the left here, we have the three decision makers or players. So Ministry of the Environment, Uniroyal, the company that caused the pollution, and down here, the local government, made up of the towns and cities and the regional municipality of Waterloo. They saw the problem the same way, so we lumped them together as one player. Then we ask, those are the key decision makers, what are the options or powers available to each decision maker in that decision? So here then, for example, the Ministry of the Environment, they only had one choice at that time. They could modify the control order, perhaps water it down a bit to satisfy the company. Uniroyal, they could delay negotiations. That means dragging your feet. You know, when you try to get a young kid to do something, you got to drag them across the floor to wash the dishes, that type of thing. They could accept the current control order, or they could abandon the plant. They actually did threaten to do that at times. They simply leave. Down here we have the local government. At that point in time, they could really only insist more strongly that Uniroyal follow the control order. So notice what we have here. We have a game with 1, 2, 3 decision makers, a total of 5 options. Now we can handle any size of finite game. We're not stuck with 2-player games like a lot of techniques are in the literature, any size. Now in practice they tend not to be too big, but we just simply continue down the list. So that's the first step. Usually it's fairly obvious. Usually we know who the decision makers are, most of their key powers or options available. Now here then is just a simplified notation. N means no, Y means yes. So notice this column here. This was a status quo when the negotiations were taking place. So what this means is no, the Ministry of the Environment is not modifying. Yes, Uniroyal is delaying. And you see it's not accepting its next 2 options. And no, the government is not insisting strongly. So this is just a summary of what happened. Then we're going to step back and take a look at a little bit of the analysis. So then the local government went from not insisting to strongly insisting. This, just for convenience, we're giving these states a number. And we get this one right here. They're strongly insisting that Uniroyal clean up the mess, start to clean it up. Now, what happened behind the scenes is that Ministry of the Environment and Uniworld, they actually formed a coalition. They recognized that this other possible resolution right here was more preferred to both of them to state 5. This here scenario, or state we call it, was more preferred by both of the top players to this one right here. So they say, there's a solution that's better for both of us. The only problem is if they acted independently, they go to a worse situation. If they act together, they can directly move to something that's more preferred. So this is what happened here. The Ministry of the Environment went from not modifying to yes, modifying. Uniworld then went from, well, they went from then not accepting to accepting, which means, of course, they no longer delay. And then the local government was still insisting. This was actually the final result in what occurred in that conflict. You can only have to guess how angry the local government was. They were absolutely furious. They were left out of those discussions because they'd spent all that money, let's say, looking at the physical systems problem, which is very good. Everybody that knew how serious it was. But when it came to strategic decision making, they want to do what's best for themselves. They had the self-interest. Somehow people like to improve themselves and do better. That's what makes the social world go around. It's sort of your value system that drives everything. Gee, I'd prefer this situation over here. Now, somebody might not want you to have that and try to block some move that you can make, but still, that's the driver, and that's why we have conflict. Differences in value systems over some issue. So value systems underlies everything when you take a system of systems approach to looking at problems. No matter what model you look at, there are always values built into it. Here, in a few minutes, I'll show you how we capture them separately for each player. Any question about that notation? If you understand that notation as I illustrate just a few more ideas, it'll sink in. So it's just a very simple notation, nice way to simply talk about the game. Instead of, for example, explaining what this state means in English, oh, gee, there we have a quick summary of it right there in the slide. Yeah, so what we'll do now, we're going to go a little bit further with this just to give you a taste of what could happen. So here it is in more detail. I already mentioned this. Here we have our 3 players. Here's what the various options mean, as I just explained. Okay, we're still at this part right here, the input subsystem right there. Now, what can happen in practice is sometimes the games can get quite large. In that case, we had 5 options, each of one which we could either accept or reject. How many possible scenarios does that make? Where are our system students? You can either accept or not accept, so it'd be 2 to the power of 5. 32 possible states. Now in practice, most of them are infeasible. If you get up to, say, 20 options, which is easy to ask, let's say from somebody who you're doing consulting for, giving them advice, that could end up at 1 million states. So size can become a problem in these games. The good news is most of the states cannot occur in practice, and one reason is, and the system prompts you for this, is they're mutually exclusive. You can only choose at most 1 at the same time. So here, for example, the entry of mutually exclusive options, Uniworld can at most choose 1 at a time. So we put 3 X's there just to keep track of that. Any state or scenario where they have more than 1 Y opposite 2, 3, and 4 is infeasible, you leave it out of the game. Simple as that. So that's how you solve that size problem. Sometimes you expect them to choose at least 1 option. They're not going to do nothing. So we put the 3 X's there to indicate they'll select at least 1, but at most 1. Indistinguishable states. This is another way to reduce the size of the game. So notice here we have a Y opposite abandon. If Uniworld abandons a plant, the dash indicates a Y or an N. It doesn't matter what the others do. All those states are essentially the same thing, so let's lump them together to simplify the game. If a company goes bankrupt, it doesn't matter if it's sales, manufacturing, research and development, the result is essentially the same. So sometimes you can lump those ideas together. Here then are the states remaining in the game. For convenience, we've numbered them from 1 to 9, but that's simply for labeling. It's no quantitative calculation. So notice that we went from 32 states down to 9. That's what we're going to use then to take a look at how to carry out an analysis. Any questions about how we got to that point there? So for example, the first state right here was, I believe, that status quo one. At that time, they were delaying the negotiations, and none of the other options were taken by this player or the other two. We actually did this analysis while it was ongoing. We had one of the interest groups from Elmira who gave us the input to the model. We did an analysis, and it came pretty close to what actually occurred. Now, we call it the graph model. What that means theoretically, we're at this situation right here. I change my option selection. I can move over to here. So you can imagine going from this node through an arc to another state. So you have a graph. Whenever you have a graph, you can automatically have a mathematical model. It's as simple as that. You simply store things in matrices. Now, with a graph, we can then say control directions if we want to. Initially, for example, we could assume that the Ministry of the Environment could go from not modifying to modifying and back again. But you might think, well, perhaps that's unidirectional, irreversible. So we then can do that. We can only allow a move in one direction if we want to. So another little ability in the model. Yeah, let me just emphasize this point right here. The whole idea of relative preferences. I guess I used the example earlier with Roy. We only require relative preference information. So up here, that's the same example I used before. You would not say, would you like to have tea or coffee have a utility value of 1.97 for coffee and 1.00 for tea. Simply say, I prefer to have coffee. Quantitative preferences, it can be useful in some calculations, but in these social disputes, they simply don't make sense, so therefore we don't assume them. We can carry this further. I'm not going to say too much about this today. We can go to, there's something called transitivity, where you rank things from most to least preferred, where you could have ties in the ranking. We can also handle something that's called intransitivity. Let's say I prefer Chinese food to Japanese because there's more variety. I prefer Japanese to German food because, let's say, it's tastier. I prefer German food to Japanese food because there's a larger, let's say, portion on your plate. So sometimes we have intransitivities when we think, and this we think arises sometimes in the real world. We can handle that no problem at all. The trouble then with some decision models, they say, well, intransitivity doesn't make sense, so let's just neglect it. Well, we disagree with that. We think it does occur sometimes. We can handle it. We might have uncertain preferences. We've looked at it on unknown, fuzzy, gray, and also probabilistic. And sometimes we have emotions. The environmentalists greatly prefer that the company not pollute the environment. So we can take that into account too. So notice we do a lot of research on preferences because this is what captures your value system here. So once again, we're working in this left branch here. When I say non-quantitative approaches, it means that we're only looking at relative preference information. So now we get to the preferences. If you use one of our decision support systems, we have a number of approaches. I'm going to show you what we mean by option prioritization. It's fine to say that you have preferences in a problem. The difficult problem is how do you actually get them so you can calibrate your model. Now, what do you think the most important thing was for the Ministry of the Environment? In this particular problem, just think back to the problem. We had then the polluting company, the Ministry of the Environment, and local government. What do you think the Ministry of the Environment, what was most important to them? This is the way you extract preferences. You simply ask, well, what's most important to you? What do you think it was for the Ministry of the Environment in this problem? Yeah.
Get the contamination down to zero.
That's very close. And that, to me, it looks like it's worth, I think I have one left. Yes. Please introduce yourself to everyone.
Okay. I'm Mary Ann Hardy, and I work at the Water Institute, supporting the administration at the Water Institute.
There's your pen. Thank you for all your hard work. That was actually very close. It wasn't quite it. We initially guessed that too when we were speaking to the expert. But actually, because the Ministry of the Environment is with the government, they did not want to see jobs lost. So they did not want the plant to leave. So it was very close. We can ask these questions in English or whatever language you speak in. And then we simply write these statements down. We call them preference statements from most important to least important. And let me just briefly show you a preference statement for one of the players. This here actually refers to the preference number. This is how we type it into the computer. -4 means not taken. So notice the Ministry of the Environment, most important is they not abandon the plant. Notice as a minister of the environment, their preferences can depend upon what others do and also them. In this case, they did not want them to abandon the plant. The second one was exactly what you said, Marianne, whereas they wanted them to accept the current control order. Now let me just translate that to English. Just take a look at this slide here. You would never show your client the numbers if you were asking what are your preferences. You'd simply write them out. So this is for most important at the top, the preference statements. So this means Minister of the Environment most prefers that Uniroyal not abandon its Elmira plant. Next, Minister of the Environment would like Uniroyal to accept the current control order, and it goes down the list. You can have if statements, if and only statements, whatever you like. For example, down here, Minister of the Environment prefers that local government insists that the original control order be applied. That means take option 5, if and only if it does not modify the control order itself. -1, do not take the first option. Now the nice thing about this is you don't have to have all the preference statements. You can just do a quick and dirty analysis where you say roughly what are the preferences of the player, but what's most important? What do you think is least important to them? Then you can take that preference information for each player and do an analysis. I'll just very briefly show you analysis in a few minutes, but you can see that that's taken in a very user-friendly way. Now one assumption we have to make here to have a simple algorithm to transfer this into preferences, we will assume transitive preferences in this particular case. So you can see that's a very nice user-friendly way to get preference information. In the course that I was teaching this term, we had the students do a project, not a project rather, but we had on one question in the assignment, go to a newspaper article that has some conflict in it, write down the main, who are the decision makers and their options, and write down the main preferences. You'll actually even see that written in the articles directly. Statements like that. So what does this mean? Let me just show you briefly. So let me go back. Minister of the Environment most prefers that Uniroyal not abandon its plant, -4. Notice here, if you take a look here, there's abandoned, that means not taken. Notice here we have all ends, that means it's a no for those states. So all of these states are more preferred than that. Here we've written the states from most preferred on the left to least preferred on the right. So notice we have all ends here. What's the next statement? Let's just take a look at one more. Next, MOE would like Uniroyal to accept the current control order, a Y opposite 3. And here we have then a Y opposite 3. Notice these states, they're further to the left, are more preferred than this set right there. And you can see what it's doing. It takes those sets, it starts splitting them up finer and finer, and eventually end up with a complete ordering of states. If not, you may get some equally preferred states, and that's fine too. So that's sort of clear then how that works. This actually was one of the best, very simple, but possibly one of the best developments in these model developments. Getting the information from the decision makers, especially preferences. Now here we have the states according to the state number from most to least preferred. There it is for Ministry of the Environment. You do something similar for Uniroyal, and likewise down here, local government. You can actually draw a graph of this if you'd like to. Here we have the states as node. Uniroyal controls a move from this state to that one over there, for example. Sometimes that can be informative. Okay, now what I want to do, I just want to show you a little bit then of the analysis and close up with a couple of overall statements. People can behave different ways under conflict, so therefore we have different stability definitions, or we call them solution concepts. How many have heard of John Nash? How many saw the movie A Beautiful Mind? Yeah, he had a very simple idea. In terms of this type of model here, all that Nash stability means, I can't improve on my own, so I might as well stay where I am. And that's a stability. We call it Nash stability. Very simple idea. It won him the Nobel Prize, by the way. Here, general meta rational. This is where I have a possible improvement. The other players can move to put me in a worse position, so therefore I'm better off not to move. When the game reaches a certain state, you ask the question, is it beneficial for me to take advantage of an improvement? If my improvements can be blocked, I'm put in a worse position, I'm better off to stay where I am. So it's a chess game. Here are different ways to think about the chess game. Here we take a look at a player has a possible unilateral improvement, and the other player can block it. The given player can't escape. Down here, this is quite a reasonable one here. Here, the other players can only block using sanctions that are improvements for them. In other words, they won't hurt themselves. Down here, limited move stability, if you put H equal to 10, let's say I'm a chess player, what's my opponent going to do? You think 10 moves and counter moves into the future. If you're worse off, you don't take that move. And this is for the infinite clever player. You can think into the infinite future. Now it ends up that's an easy problem to solve because you get cycles. As soon as the cycle repeats, of course, you've already solved it. But the useful ones are probably these top 4, especially sequential stability. So if you have a computer program, we have the conflict model, decision makers, options, preferences. Then we have the computer calculate everything here. Here then, we're at a given state. Let's say it's this one right here. And we're looking at it from local government's point of view. So the local government controls this one right here. So from this state, they go from an N to a Y. That's a unilateral improvement. 8 is more preferred to 4. Notice only the local government is changing its option selection. Then we ask, can the other player move to block it? Well, then there's a move by Uniroyal. This is where Uniroyal then goes from not accepting to abandoning the plant, and they move the game over to here. 9 is less preferred to 4, therefore that unilateral improvement is blocked. So that's an example of how the thinking goes when you look at these moves and counter moves. So think of it like a chess player. When we do an analysis, the first thing, what is the best a given player can do on his or her own? Then we ask the question, can you do even better using coalition analysis? And then we've done a lot of work in coalition analysis. The answer is often yes. There was a simple example in the Elmira conflict where the first 2 players move together, they end up at a better position. We have then equivalent definitions when we look at coalitions. In other words, they can move together to make themselves better off. Here then, for example, is this game once again where we were at state 1. Then the local government went from not insisting to strongly insisting. And then we had a coalition right here where they went from not modifying to modifying the control order. Uniroyal accepted. That's what we call a joint unilateral improvement because state 8 was more preferred to 5 by both players. Here's sort of the current situation with respect to this pollution problem. All the wells in Elmira are still closed and water continues to be shipped from the city of Waterloo to Elmira. And let me think, that was about how many years ago? 27 years ago or so? Quite a few years ago. It's still ongoing. They pump water up from underground, they treat the water from underground, from the aquifer, then put it into the local creek, and all the chemicals coming out of the plant of this type are treated in a very simple way. It's actually very easy to treat these chemicals. So that's ongoing. The trouble with these groundwater pollution problems, you don't know how long it's going to last. See, is Simone here still? She might have had to leave earlier. Anyway, she took a look at the current conflicts in Elmira, where they're worried now about the stream outside of the chemical plant and what's happening there. So we've actually written a paper on that too. But this one was more or less solved. The parties are satisfied, but they're recognizing there are other pollution to clean up too. There's where home hardware started in Elmira, Ontario. There was a student group that went up to visit. Once Mark Servos is in the group there. So that's often a nice example of groundwater pollution, which they show to the civil engineering and environmental engineering students. We do have a new book which has just come out. This is one of 3 books we've written on this topic. You can download that free of charge, by the way, if you go to our library, instead of paying $300. Let me just mention some of the extensions briefly, and then I'll finish off. Here's some of the research that we're taking a look at on certain preferences, very important. Psychological factors, we've operationalized a lot of these ideas. What if I have a neutral attitude, positive attitude, or negative? We've actually operationalized that. You can carry out an analysis when you do that. You would expect if you have a positive attitude, you get a better result, and the answer is yes. A lot of applications, we use that for all of our motivation. Here's what we're looking at the current time. You can think of 3 different systems perspectives. Here then we have the input, remember the Elmira model, decision makers, option preferences. The engine, this is where you look at the moves and counter moves in different ways. It's stable for all the players, it's an equilibrium at a given state. And the output, the individual stability and the possible resolution. Here's what we call the inverse engineering problem. What if there's a desirable equilibrium that we want? It's, for example, let's say if you're looking at it from a societal point of view, it happens to be where they clean up the pollution. What do the preferences of one or more of the decision makers have to be in order to reach that result? That's the inverse problem that is actually asked. Here's what we call the behavioral problem, or behavioral engine problem. We know the input, we know the output. How were those players thinking in order to bring that about? What was their psychology under conflict situations to do that? So this is really an artificial intelligence problem. Machines think intelligently like people, such as learning and problem solving. That's the definition of AI. So in inverse engineering, for example, inverse GMCR, we have a computer program that determines how people should think to reach a desirable result. So you're trying to program the computer to think how people may think in practice. So we think it does have a big role to play. It ends up, for example, in the inverse engineering problem, you get a lot of possible preferences that could occur. So you get a really big size problem when you start taking a look at that. Another way to take a look at it, creativity and conflict resolution. Learning how a decision maker may think. It could be by error and trial. It could be by the actions of others. One student, Amanda, I don't think she's here right now, you see a player in a game doing a certain action. Under the assumption the player might be doing something that's beneficial to him or her, can you keep track of that and transfer that into preferences, knowing they may think in a certain way? What ends up, we've solved it mathematically, some of these problems, but it does become sort of an AI type of problem. You get so many solutions. But still, we can handle that theoretically. Creativity, for purposely directing this thinking to reach win-win resolutions. How do we do that in order to get a better result? Some of it is related to inverse engineering, as I just mentioned. Okay, overall, what we think of in our research overall, we're really trying to think about responsible governance. Take a system of systems perspectives. We have all these interacting systems. You have to take that into account somehow. You want to be integrative. We want to be adaptive. We know in systems theory that you can have emergent properties or surprises. How are you going to handle those in a good way? And very importantly, we want it to be participatory. Reflect the values of the stakeholders. Very important. If you come up with a policy or an agreement where you do not reflect the value systems of the stakeholders involved, it's not going to last. As simple as that. Donald Trump thinks that zero-sum games solve the world's problems. Give it all to me. In fact, they don't. That's a recipe for failure. Now, what's really nice overall is we want to achieve desirable system goals such as resiliency, sustainability, and fairness. Now, doesn't that sound a lot nicer than saying, well, we got to increase the gross domestic product by 5% this year? I mean, that's really a way to turn somebody off. So that's why when you think in terms of systems thinking, you can come up naturally with sort of ethics and value systems. It just flows out of that type of mentality. Let me just close by mentioning we're going to be having a conference in Nanjing. As Professor Panamala mentioned earlier on, these conferences started right here in Waterloo in 1993. The Water Institute is heavily involved with this, and we're hoping to make it one of the best water environmental conferences ever in China. So we invite you to consider submitting a paper to this. I think they can click to this on your website, right, Roy? Yeah, if you go to the website then of the Water Institute, you can see it right there. The extended abstracts are due at the end of the year. But we're going to have a lot of really interesting problems. There are a lot of sessions, for example, in climate change. Others might deal with methodologies, for example, economic approaches to looking at these problems. It's going to be a really systems approach to looking at these types of environmental problems. So I think I'll stop right there, Roy.
Thank you very much, Professor Hipel. Thank you very much. Some questions. Kevin.
Thanks very much, Keith. That was fascinating. I've got a simple question. Does game theory allow for losers? In other words, can there be, you talk about the preferred solution reflecting the values of stakeholders. Well, are there stakeholder groups that can absolutely lose under the best case scenario? And my second question is, do you have any comments on the pipeline issue in Canada?
Well, I do the second one, but let me start with the first. Yes, definitely there can be losers, because what happens is in the game, everybody's instinctively trying to satisfy their own values, their own self-interest, let's say. But you usually have enough power that the other side might not get their best result, and you might not get yours. So sometimes it ends up, compromise might be the wrong word, but some type of compromise situation. Other cases, it could be a zero-sum game. No matter what you do, you're going to end up in a worse position. For example, let's say something like Poland, just before the Soviet Union collapsed. Well, if Russia ever invaded Poland, they would certainly be the losers. That's for sure. So they tried to do everything, of course, to avoid an invasion by Russia. So it goes all the way from, let's say, a zero-sum game, I get it all and you get nothing, that type of thing, to the situation where everybody benefits, and also then get into coalitions where you're purposely trying to make sure that everybody benefits within the coalition. Now, the pipeline one is a very good, interesting one. I'm glad you brought it up. My talk in Halifax a few weeks ago, I did bring up that problem. First of all, you got to go to the literature. The best economic literature on the pipeline debate and exportation of oil came out by the Canadian Academy of Engineering. They had a couple of excellent reports. And let me just explain it. With the extended pipeline to the United States, was the extended Keystone pipeline, and let's say the one going from the west to Vancouver, an expanded pipeline there, if we export in the volumes, excuse me, that we were thinking of, our loss per year is $60 billion of value added. The Canadian Academy of Engineering believes that we should be refining all of this in Canada. A refinery then costs almost nothing. They're only about $15 billion. If you're losing $60 billion a year of value added, why wouldn't you do it? Another thing related to that issue, if you have control and you control the refining, that means you get all the spin-off products. All they're talking about now is don't burn oil and fossil fuels. But there are a lot of other chemicals and things that we really need in society, paints and all the rest of it. If you refine everything there, you're also adding the value added that will stay on for a long time, basically forever. And that's what we want to do. So what the government should be doing now, they have a very big opportunity. Two things. Number one, I think Trudeau's doing an excellent job when it comes to cutting back in emissions. In a sense, he said to the provinces, if you don't cut back, we're going to tax the emissions ourselves. We'll give the money back to the provinces to use for useful purposes, but we're going to do it. That's the right approach. The only drawback there, it's not tough enough. We need bigger cutbacks at the present time. So that's really good. Number two, there's a very valuable opportunity here. See, in Saskatchewan, Manitoba, and Ontario, we have conservative governments. They are pro-pipeline, and that is, by the way to go. You bring the bitumen from Alberta to Sarnia, later on extend it to Quebec City, Montreal, and St. John's. You bring it by pipeline and you make sure all the value added is done here. Then you have real control when you cut out the burning of fossil fuels and make sure you have a real thriving industry left that makes all the value added products. So what an opportunity we have right now. I did mention that in Halifax. It's just a golden opportunity to do everything right. So let's hope the government bites and they don't lose this opportunity. Yeah. I hope that answered your question. Yeah.
Thanks for keeping this topic very interesting. I guess I'm curious about what kinds of judgments go into operationalizing the different things that you operation, attitudes, emotions, even things like fairness. Like there's different models of fairness, right? We can talk about a fair outcome for everyone, or we can talk about fairness in terms of relative outcomes for everyone. So how do those kinds of considerations get made?
Yeah, excellent question. What you have to do is very clearly define what you mean by fairness in a certain situation, so everybody's thinking about it the same way, and then we can operationalize that within models. So for example, if you join a coalition, you don't want anybody to be worse off from joining. You're cooperating to solve a problem, let's say. Make sure that nobody's worse off. Maybe some will be a bit better off. There are different ways you can define it exactly, and that's what's done in cooperative game theory. They have different ways to define fairness, but it's roughly the way you would say it in English and any other languages, but you have to be precise. So in that water allocation model that I mentioned there, we can explain exactly what fairness means. The one, let's say, user may say, well, why are they getting that and I'm not getting this? Well, to start with, the model is actually 2 steps. First step is you got to make sure that it's fair according to the agreements that were in place. It might be first come, first serve. Whatever it happens to be, more upstream. Maybe there's some agreement to share it downstream beforehand. Then you take a look at what did the stakeholders have in water that's still available that they could somehow, let's say, sell to the others in order to make the system better off overall. And you can do that for both the demand side and supply side. He up there is sort of looking at the demand side right now, some of the problems that arise there. But we've applied that to the South Saskatchewan River Basin, to the Aral Sea in the Middle East. And these methodologies are actually operational. And you can go in there and explain, well, this is why it's fair according to the way we set it up. Yeah, so you have to be precise. That's why you want to have a model when you talk about these things. Otherwise, you just sort of argue back and forth. Right?
I'm a philosopher, so I get it.
Yeah. Okay, good. What type of philosophy?
Socially relevant philosophy of science.
Huh, okay, very interesting. Oh, we'll have to have a continued discussion
Yes.
with Roy at the grad house. Yeah.
I propose we stop the lecture here. Let's give Professor Keith Hipel one more time a big encouragement. Thank you so much.
Yeah, thank you.
Congratulations once again.